Electromagnetic waves. Physical Sciences, Grade 10. In the last video, we learned about electromagnetic spectrum, which consists of different types of electromagnetic radiation. Electromagnetic radiation is carried out by electromagnetic waves. But where do electromagnetic waves come from? Electromagnetic waves come from accelerating charges. That is the answer. Sweet and simple. Charges can be negative or positive. For an object to be accelerating, it means that it is either that the speed of the object is changing. This means that the speed is increasing or decreasing, or the direction in which the object is traveling is also changing. So even if the speed is constant, as long as the direction is changing, we say that that object is accelerating. This means that accelerating charges are charges that are changing speed or direction. These charges, as they are accelerating, they emit or release electromagnetic waves. Charges such as electrons and protons are always spinning round and round and round a type of dance. This means that their acceleration is changing, so they are accelerating. And this means that they are able to release or to produce or to emit electromagnetic waves. You will notice that an electromagnetic wave is made of an electric field and a magnetic field, hence electromagnetic wave. These two fields are always perpendicular to each other and to the direction of propagation. The entire wave is moving like this, in this direction. And the magnetic field and the electric field is pointing in this direction. And the magnetic field is pointing in this direction. These three directions are perpendicular to one another. This means that there is a 90-degree angle between them. At the end of this lesson, it is my biggest hope that you are able to describe where electromagnetic waves come from. Describe how electromagnetic waves propagate or travel. State that electromagnetic waves have a speed, a wave speed c, which is equals to 3 multiplied by 10 to the power of, or raised to the power of 8 meters per second in vacuum. Use the wave equation to perform calculations relating to electromagnetic waves, and explain that some aspects of the behavior of electromagnetic radiation can best be explained using a wave model, and some aspects can best be explained using a particle model, something called wave-particle duality. Define a proton. Last but not least, calculate the energy of that photon. Accelerating charges produce a continuously changing electric field, or they create a continuously changing electric field. This continuously changing electric field induces or creates a continuously changing magnetic field perpendicular to the electric field. So the electric field and the magnetic field are perpendicular to each other. The combination of the magnetic field and the electric field creates what we call an electromagnetic wave. This means that an electromagnetic wave propagates when an electric field changing in one plane produces a magnetic field changing in a plane at right angles to that of the electric field, which then also produces a changing electric field, and so on and so on. So an electric field creates a magnetic field. A magnetic field in return creates an electric field. An electric field in turn creates a, a magnetic field, on and on and on and on. And that's how an electromagnetic wave propagates or travels. Propagation of electromagnetic waves can be described as mutual induction. The changing electric field is responsible for inducing the magnetic field, and the changing magnetic field is responsible for inducing the electric field. So they mutually induce each other. Electromagnetic waves have properties that are common to all of them. For example, all electromagnetic waves come from accelerating charges. All electromagnetic waves propagate as an electric field and a magnetic field, which are perpendicular to each other and to the direction of propagation. All electromagnetic waves can travel through vacuum, that is empty space, at a speed of c, which is equals to 3 multiplied by 10 raised to the power of 8 meters per second. When an electromagnetic wave travels through a medium, it travels slower than it would in empty space or vacuum. Since electromagnetic waves or electromagnetic radiation is a wave, the following wave equation still applies. In the earlier videos, we learned that the speed v of a wave equals to the frequency f of a wave multiplied by the wavelength lambda of a wave. However, for electromagnetic waves, the speed v is replaced with c, which is the speed of electromagnetic waves or electromagnetic radiation in vacuum. So when we replaced v with c, we are left with that the speed c equals to the frequency f multiplied by the wavelength lambda, whereby c is the speed in vacuum, where c equals to 3 multiplied by 10 raised to the power of 8 meters per second. Lambda is the wavelength in meters. F is the frequency in hertz. We can use this triangle to remember this equation or this formula, whereby we know that C equals to F multiplied by lambda. This also means that F equals to C divided by lambda, whereas lambda equals to C divided by F. An electromagnetic wave has a wavelength of 200 nanometers. Calculate the frequency of the radiation. We are given that the wavelength is 200 nanometers. This means that we need to convert the wavelength from nanometers to meters, which are the SI units for wavelength. A nano simply means 10 to the power or raised to the power of -9. This means to convert 200 nanometers to meters, we will simply say that the wavelength equals to 200 multiplied by 10 to the power of -9 meters. We are not given necessarily the speed of the electromagnetic wave, but we know that electromagnetic wave in vacuum have the same speed, which is c equals to 3 multiplied by 10 raised to the power of 8 meters per second. What we have to do is to calculate the frequency of this radiation, and the SI unit for frequency is hertz. So we will solve this problem using the wave equation, which is as follows: that C equals to the frequency F multiplied by the wavelength lambda. So we need to rearrange the terms because we're not trying to solve for the speed, we're trying to solve for the frequency. So we will use this triangle over here where it says that the frequency of an electromagnetic wave or radiation equals to C divided by lambda. So the frequency F equals to C divided by lambda. And now it is just a matter of substituting the known values of the speed of electromagnetic radiation as well as the wavelength of this electromagnetic radiation. So we'll have that the frequency F equals to 3 multiplied by 10 raised to the power of 8 all divided by 200 multiplied by 10 raised to the power of -9. And the answer is that the frequency equals to 1.5 multiplied by 10 raised to the power of 15 hertz. I have said repeatedly that electromagnetic waves are waves. And now I'm about to tell you that electromagnetic waves can also be particles. This means that electromagnetic waves have a wave nature and a particle nature. But how can something be a particle and a wave? Electromagnetic waves have both wave-like and particle-like properties, something called wave-particle duality. Sounds very fancy, ne? Wave-particle duality. Does this sound confusing? Well, I'm about to confuse you even more. Electromagnetic waves have both wave-like and particle-like properties, but only show one or the other depending on the kind of experiment that you are performing. So, if you are performing a wave type experiment, the electromagnetic waves will show its wave nature. However, if you are performing a particle type experiment, the electromagnetic radiation will show its particle nature. One cannot test the wave and the particle nature of electromagnetic waves at the same time. We have already spoken about the wave nature of electromagnetic waves, and now we turn our attention to the particle nature of electromagnetic waves. A particle of electromagnetic radiation is called a photon. A photon is a quantum, or it is like a packet of energy, quantum. Electromagnetic waves transfer energy store other matter in packets of energy called photons. Photons have a set amount of energy, and that energy is called a quantum. The energy of a photon can be calculated using the following expression. E equals to hf, where E is the energy of the photon in joules or J, F is the frequency in hertz, and H is the Planck's constant, which is equals to 6.63 multiplied by 10 raised to the power of minus 34 joule seconds, or J dot S, that is joule seconds. Now, since we said that the speed of an electromagnetic wave C equals to the frequency of the electromagnetic wave multiplied by the wavelength of an electromagnetic wave, we can use our triangle to realize that F just equals to C divided by the wavelength lambda. So the frequency F equals to C divided by the wavelength. And if we substitute the F equals to C over lambda into the equation to calculate the energy of a photon, which was given to us as E equals to hf, we are left with that E equals to H brackets C divided by lambda. So the energy of a photon equals to Planck's constant multiplied by the speed of electromagnetic radiation divided by the wavelength of electromagnetic radiation. We have already mentioned what E is the energy in joules, H is the Planck's constant, and C is the speed of electromagnetic radiation in vacuum. And now lambda is just the wavelength in meters. Calculate the energy that an ultraviolet ray photon of wavelength lambda equals to 250 nanometers transfers to a human cell. We are given that the wavelength equals to 250 nanometers, which we can write as 250 multiplied by 10 raised to the power of minus 9 meters. Nano just means 10 raised to the power of minus 9. We know that the speed of each type, the English is going away. So the speed of electromagnetic radiation is equals to 3 multiplied by 10 raised to the power of 8 meters per second. And H is the Planck's constant, which is equals to 6.63 multiplied by 10 raised to the power of negative or minus 34 joule seconds. And we must calculate the energy, and that energy we must report it, or its SI unit is joules. So we solve using that equation on how to calculate the energy of a photon. From here, it's just a matter of substituting the correct values or the known values of the other terms. It is very important when you are using your calculator to use brackets. Brackets are your best friend. Brackets love you, because when you are working with very small numbers, such as Planck's constant, and very large numbers, such as the speed of electromagnetic radiation, your calculator, it doesn't get confused, but remember it uses BODMAS. You learned about BODMAS in later grades. So that's why I've put everything in a bracket. Every physical quantity has its own brackets. This makes sure that you calculate the correct value. So the energy of this photon equals to 6.63 multiplied by 10 raised to the power of minus 34, and the whole thing is multiplied by 3 multiplied by 10 raised to the power of 8, both of which are divided by 250 multiplied by 10 raised to the power of minus 9. And the answer there is that the energy of this UV photon equals to 7.96 multiplied by 10 raised to the power of negative 19 joules. We have come to the end, and we've learned a lot in this lesson. We've learned that electromagnetic waves come from accelerating charges, and that electromagnetic wave, when they travel or when they propagate as an electric field and a magnetic field, which are perpendicular to each other. We've also learned that the speed of electromagnetic waves in vacuum, it is equals to c, which is 3 multiplied by 10 raised to the power of 8 meters per second. We've also learned that a particle of electromagnetic waves called a photon is just a packet of energy, and this energy we can calculate, and that energy is directly proportional to the frequency and inversely proportional to the wavelength. So if the energy of the photon is high, the wavelength will be short, but also the frequency will be high. If the energy of an electromagnetic radiation is low, the wavelength will be long, but the frequency will also be high. Thank you so much for watching.